Welcome to lectures of Power System Dynamics and Control course. So this is your lecture where we'll continue the small signal stability analysis. So in the last class, that is yesterday, we discussed about the modal matrix, how we can use the modal matrices in stability analysis. Particularly, we discussed those right eigenvector matrices and left eigenvector matrix and also participation factor matrix, right? So we'll continue with this and we'll discuss one example, and also we learned how to linearize the nonlinear differential equations, right? So today we'll continue with small signal stability analysis of single machine infinite bus system, SMIV. In fact, we'll talk more about SMIV with different representation of the synchronous machines. Like first we'll consider here the classical model. Classical model already I told you. Classical model means that is the constant flux linkage model where everything is neglected. In fact, the governor dynamics, the time constants, all the time constants, subtransient and transient time constants, they're all neglected. And only we are considering the swing equation in the classical model to solve this. So first we'll discuss the SMIV, small signal analysis with SMIV, considering the classical model representation. Okay. So this is a single machine infinite bus where one generator is connected to the large system where it is assumed that this large system is swinging uh, synchronously and this generator is connected to this large system. So any disturbance taking place between this generator and the large system, the behavior of the stability of the behavior in terms of the stability of the generator will be studied in this case, right? So here this generator is connected through the series transmission lines and with two parallel transmission lines as well, Z4, Z5, right? And these are the charging impedances. And Z1, Z7, there are also two transmission lines, right? Now, if we'll find the equivalent impedance of this whole network, it is possible to find. So I can just simplify this circuit, the generator connected to the infinite bus with this equivalent impedance, Z equivalent, that is equal to Re plus JXE. Okay, so this is your single machine infinite bus system. By simplifying this network impedances. Now let us see the generator represented by the classical model. We'll start with the classical model, then we'll gradually go with representation of different other models. Okay. So now for the classical model, it is assumed that the resistances of the network impedance is neglected, and also the resistance of the synchronous machine, internal resistance, that is RS, is also neglected. Only XD dash is considered, that is transient direct axis reactance, right? So we can see now the equivalent circuit where E dash delta represents the internal EMF of the generator, and IT is the terminal current, and EVO is your infinite bus voltage. Okay, so this is in fact the reference of the network, EV0, right? So now if we'll find the equivalent impedance or equivalent reactance, that is XT, that is nothing but J of XT dash plus XE, right? So therefore I can write XT is equal to XT dash plus XE. And E dash, obviously E dash is nothing but ETO plus J of XT dash ITO, right? So this is E dash is the internal voltage, and ETO is your base voltage, or under steady state condition, what is the terminal voltage here, ETO, plus J of XT dash ITO, right? Now if I'll find IT, that is the terminal current, that is obviously it will be E dash delta minus EB 0 divided by XT, right? JXT. But if I'll somehow represent in other way, if I'll take E dash as reference, then EB will make an angle of minus delta, right? So making, just to simplify the calculation, if I'll consider E dash as the reference, so it will become E dash 0 because it is reference, minus then EB will make an angle of, because E dash is making an angle of delta with respect to EB. Now if we'll draw the phasor diagram, you can understand it better. So this is your EB reference phasor. This is E dash making an angle of delta. Now if I'll change the reference is changed from EB to E dash, then what will happen? EB will make an angle of minus delta with respect to E dash, right? It will make an angle of minus delta with respect to E dash. So therefore it is written here E dash 0 minus EB minus delta, right? That is equal to E dash minus EB cos delta minus J sin delta divided by JXT. This arrangement is made just to simplify the calculation, nothing else. Okay. So now if we'll write the expression for complex power S dash. So what is the point in writing the complex power expression? Because I need to find the expression for real power P, which is equal to the torque, electromagnetic torque developed. So the complex power, I can write it as P plus JXQ, that is equal to E dash IT star, right? So this is nothing but, IT star is nothing but, if I'll substitute this expression here, it will become E dash EB sin delta by XT plus J of E dash multiplied by E dash minus EB cos delta by XT. So now I can find the expression for real power generated or injected to the network is E dash EB sin delta by XT. Okay. So that is in power unit, it is equal to TE, right? We know this from the previous analysis. T equal to P, that is equal to E dash EB by XT sin delta. So if I want to find a small change in T, that is delta T, so I can find it just by taking the partial derivative, evaluating at the initial condition. Initial condition is nothing but this is your delta naught, right? So then delta T by delta delta into delta delta, that will give me, just by taking derivative and evaluating it at delta naught, we'll find E dash EB by XT cos delta naught into delta delta. Delta delta will remain as it is. Okay. So now this is your delta TE. So we know the swing equations. The swing equation, if I'll write, this is your swing equation, right? D by dt of delta omega. This is the change in speed deviation. That is equal to 1 by 2h Tm minus T by Kd delta omega r. And another equation obviously constant to the speed, that is d by dt of delta will be equal to omega naught delta omega r, right? So where delta omega r is the per unit speed deviation and delta is the rotor angle, right? So now if we'll linearize these two equations, what we'll get? D by dt of delta omega r, that is equal to 1 by th delta tm. Just we can use that we discussed in the last class how to linearize a nonlinear equation. You can just apply that method. By applying that method, that process, will find 1 by 2h delta Tm minus Ks delta delta minus Kd delta omega r. So this case delta delta I have substituted instead of delta Te, right? So already we have derived delta Te is equal to E dash Eb by x. We can see it here by xt by xt cos of delta naught, right, into delta delta. So delta delta will remain as it is, and this term is nothing but it is equal to Ks, a constant, right? And minus of Kd delta omega r, then dy dt of delta delta will be equal to omega naught delta omega r. So Ks is equal to E dash Eb by xt cos delta naught. Okay. Now from these two equations, if I'll write the state space model, that will be nothing but d by dt of delta omega or delta delta, that will be equal to minus kd by 2h minus ks by 2h omega naught 0. This is your state matrix, or you can say plant matrix, and delta omega r delta delta plus 1 by 2h 0 delta tm. This is your input. Okay, control input here. And now if I'll plot the block diagram for this state space model, transfer function block diagram, it will look like this, right? This is your, this k is in fact known as synchronizing torque coefficient. Like kd is known as damping torque coefficient. So ks is also known as synchronizing torque coefficient. So if we'll plot the transfer function block diagram, it will look like this, right? So you can draw this, it is easy, it is in fact easy, so you can do it. So now from this, if I'll find the characteristic equation from this A matrix, and from the characteristic equation I can find omega n, that is the natural undamped frequency, that I'll find it as follows: Ks omega naught by 2h square root, and your damping ratio zeta will be equal to half of kd by 2h omega n. That will be in fact equal to 1 by 2 kd by ks 2h omega naught square root. So this is omega expression for omega n and damping ratio from this state matrix, right? If we'll derive the characteristic equation, from the characteristic equation we can find omega n and zeta, the expression for omega n and zeta, right? Then we can do further analysis for finding the eigenvalues, then your right eigenvector matrix, then your left eigenvector matrix, then participation matrix, right? Participation factor matrix. All these things we can find, and we can do model analysis on this. So let us do one example on this, and we can see it how it is very easily we can accomplish to find the stability of the system, to know the stability of the system, and also we can find the time domain response as well for delta delta and delta omega r. So in fact this is a single mesh in infinite. It is not a single mesh in infinite system. We have here 4 machines in a particular power plant. If we'll consider a particular power plant, it has a 4 machine system. There are 4 synchronous generators rated at 555 MVA, right? And here equivalently we are considering that all the 4 machines are coherently, they are synchronized with each other and they are operating in a coherent manner. So therefore I can consider the whole plant as a single machine system having the MVA rating 4 into 555 MVA. Okay. So now this whole plant is connected through a transformer and through the transmission line to the infinite bus. Okay. So there are two parallel transmission lines with these reactances. Okay, and the transformer having the reactance in power unit 0.15. Okay, so now the question, okay, so the network reactance is shown in the figure are in power unit. These are in power unit on 2220 MVA. This is nothing but this is the base rating of the power plant, right? 4 into 555 is nothing but 2220 MVA, right? And 24 kV is your LT side voltage of the transformer, and your high voltage side voltage is not given. So therefore, this power unit calculation has been made considering the power rating of 2220 MVA and 24 kV base, referred to LT side. Okay, so and the resistances are assumed to be negligible here. It is neglected. So the objective of this example is to analyze the small signal stability characteristic of the system about the steady state operating condition following the loss of circuit 2. So when the circuit 2 is lost, that means this circuit is lost. Under that condition, what will be the steady state stability or the small signal stability of the system? That is the point to discuss here. Therefore, we need to find the initial conditions just after the removal of this circuit. Okay, so therefore it is mentioned here the post fault system condition in power unit on this base on 2220 MV and 24 kV base is as follows. So the power unit power injected to the infinite bus is 0.9, and power unit reactive power injected is 0.3 overexcited condition. So it is in fact providing reactive power to the grid, that is overexcited condition. If the generator is underexcited, it will draw the reactive power, right? So, and your terminal voltage ET here, it is already mentioned there. It is 136 degree, right? And EB is the infinite bus voltage, that is given 0.9950 degree. Because this is the reference, so therefore it is 0.9950 degree. Now, the generators are to be modeled as a single equivalent generator. So considering the whole plant as single equivalent generator, so therefore the rating becomes 4 into 555 MVA. And as the classical model is being used to represent this generator, therefore XD dash is 0.3 given, that is in power unit, and H is given 3.5 megawatt second by MVA. Okay. So now the question is, we need to write the linearized state equations of the system and then determine the eigenvalues, damped frequency of oscillation, that is omega d, right? And damping ratio, that is zeta, and undamped natural frequency omega n for each of the following values of the damping coefficient. So these damping coefficients are given: kd equal to 0, kd equal to -10, and kd equal to 10. For each of the kd value, we'll see what is happening to these values, and also we can see whether the system is in fact stable or not. So for the case with kd equal to 10, second question is, for the case with kd equal to 10, find the left and right eigenvectors and participation matrix. Determine the time response if at t equal to 0, delta equal to 5 degree and delta omega is equal to 0 degree. That means this is your initial condition. Using this initial condition, we need to find the time response. Okay, so Let us do this problem. So you know this damping coefficient, when it is becoming negative, obviously your system becomes unstable. When this KD is positive, it is giving the damping torque to the system. That means your system is going to be stable. Let us check it with this, and if KD equal to 0, maybe your system is undamped and it is oscillatory. We'll see it. Let us see. So if we'll see the following figure here, the circuit model representing the post-fault steady state operating condition with all parameters that is expressed in power unit on 2220 MVA base will look like this, right? So your E dash delta and EB, ET is given, EB is given, your reactances are given. In fact, E dash is not given, we need to find it out. So with ET as reference phasor, let us consider ET as reference phasor in order to make our calculation simpler. The generator starter current or the terminal current can be given by this. Okay. So P plus JQ conjugate divided by the terminal voltage conjugate. So that will give me 0.9 minus J 0.3 per unit. So the voltage, now if we'll find the voltage behind the transient reactance, that is the internal EMF of the generator, E dash, that will be equal to ET plus JXT dash IT. Just by putting or substituting the values, I can find the E dash, that is your internal EMF. So E dash becomes 1.123, 13.92 degree. This 13.92 degree is the angle with respect to ET, because we are considering ET here as the reference, right? If I'll plot it ET here, then your E dash is here somewhere, right? So this is making an angle of 13.92 degree. Okay. And the angle by which E dash leads EB will be found. So EB is in fact making an angle of 36 degree. If we'll plot it EB, so ET is making an angle of 36 degree with respect to EB, right? So therefore now E dash will make an angle of 13.92 plus 36 degree with respect to EB, right? So that is what the angle by which E dash leads EB is. That is equal to delta O. That is the initial value of the delta. 13.92 degree plus 36 degree, that is nothing but is equal to 49.92 degree. Okay. So now the total system reactance will become XT. So XT will be nothing but will be equal to addition of or sum of all the reactances. That is 0.3 plus 0.15 plus 0.5, that will give me 0.95 per unit. And then we can find the corresponding synchronizing coefficients. Then synchronizing torque coefficient, I can find E dash EV by XT cos delta naught. Delta naught I know, now substituting these values, I'll find 0.757 per unit torque, right, per radian. So now if we'll present the linearized system, already we derived this system. This linearized system of equation for the classical model of the SMIB, single machine infinite bus system, that will look like this. Delta omega r dot delta delta dot will be equal to this A matrix consisting of minus KD by 2H minus KS by 2H. Then omega O 0, right? And your state vectors is delta omega r, change in speed, and delta delta plus your B matrix is 1 by 2H 0 and input is delta Tm. So now substituting the respective values of 2H, H and omega naught, delta naught, everything, we'll find here minus 0.143 Kd, because Kd is a variable and we know for different values of KD we need to find omega n, omega d, zeta, and the eigenvalues. So therefore, if we'll keep this KD as it is, your state matrix will look like having elements minus 0.143 KD, minus 0.108, 377 omega O, and that is 0. So then your B matrix will become 0.1430. Now we can find the eigenvalues of the state matrix. So in order to find the eigenvalues, we need to find the characteristic equation of the state matrix. So that characteristic equation is nothing but it is equal to the determinant of the state matrix. Sorry, determinant of the state matrix minus A minus lambda I, right? A minus lambda I. So if we'll find the determinant, it will look like this: lambda square plus 0.143 KD lambda plus 40.79 equal to 0. So this is in fact your characteristic equation, right? Characteristic equation. And from this equation, I can find omega n, right? Omega n, zeta, and omega n can be found from here, right? From 40.79 square root. I can find then zeta from here. Zeta will be having expression of 0.0112 KD, right? Then I can find omega d also. So before that, let us find the expression for lambda 1 and lambda 2. This is minus zeta omega n plus minus omega n square root 1 minus zeta square. And omega d is nothing but omega n into 1 minus zeta square square root. So these values, if we'll see these expressions for omega n, zeta, omega n is obviously constant, 1.0165 Hodge. Zeta, lambda 1, lambda 2, omega d, they're all in fact the function of KD, right? So therefore we need to evaluate zeta, lambda 1, lambda 2, omega d at different values of KD. So now in this table, it is shown for KD of 0, 10, and minus 10, the values of eigenvalues, damped frequency, zeta, omega n obviously it will remain constant, is evaluated. Now you can see the eigenvalues when KD equal to 0, it is plus minus j 6.39. We can see here the real part of this eigenvalue is 0. Therefore, the system will become oscillatory under when KD equal to 0, right? When KD equal to 10, that is positive value, then your eigenvalue has negative real part, right? That indicates that your system is asymptotically stable, right? And for KD equal to minus 10, the real part of the eigenvalue is becoming positive here. So therefore, it is aperiodic unstable, right? So this is they're not stable, right? It is the system becomes unstable. Then we can see the values of damped frequency omega d for different values of KD, right? This is omega d. Then the damping ratio also evaluated at different values of KD. This is 0, then 0.112 minus 0.112, right? So this is from this we can get the information of stability. Now we'll find the time domain response. So the question in the part B is to find the time domain response when the initial condition is given, right? So in order to find the time domain response, also the question says to find the right eigenvector, left eigenvector, and the participation matrix. So let us evaluate those right eigenvector matrix, left eigenvector matrix, and then your participation factor matrix, right? So this is the equation from where we can in fact find the right eigenvector matrix. And for this case, the value of KD is given 10 here. And now the above equation can be written just by substituting ith lambda, let us say a general value of lambda, lambda I in this equation. If it will be substituted lambda I, then the equation will look like minus 1.43 minus lambda I minus 0.108 3770.0 and minus lambda I, that is multiplied with the ith eigenvector, right eigenvector, that is phi 1i, phi 2i, right? So if it will be equated to 0, we'll have two equations now. If we'll substitute one value of lambda, let us substitute lambda equal to lambda evaluated at KD equal to 10, we'll have two values. So one of the value will be minus 0.714 plus J 6.35. Then the corresponding equations, if we'll substitute this lambda in this equation, then we have two equations now, and it will become 0.714 plus J 6.35 511. So I have substituted here I equal to 1, right? So therefore lambda 1 is here. This is your lambda 1, and your eigenvector corresponding to lambda 1 will be phi 11 and phi 21. So therefore we'll have two equations, these two equations, and these two equations, if we'll see, these two equations are independent of each other. They are not dependent with each other, right? So now in order to solve these independent equations, we have to assume the value of one of the value of the eigenvector, one of the element of the right eigenvector corresponding to lambda 1, right? So therefore we assumed phi 21 as 1 here. Like last class also we discussed one RLC circuit where we assumed one of the element of these eigenvectors as 1, right? So here we are assuming phi 21 as 1. Then considering this value of phi 21, we can find phi 11. So phi 11 will be calculated as minus 0.0019 plus J 0.0168. Okay. Similarly, the eigenvector corresponding to lambda 2 can be found. So another eigenvalue lambda 2, that is equal to minus 0.714 minus J of 6.35. So if we'll evaluate considering those two independent equations, we'll find phi 22. Assuming phi 22 as 1, we'll find phi 12, that will be equal to minus of 0.0019 minus J of 0.0168, right? Then the right eigenvector model matrix will become this, right? So this is your phi 1, this is your phi 2. Okay, so phi 1 is this, that is the right eigenvector corresponding to lambda 1, and this is phi 2, right eigenvector corresponding to lambda 2. Okay, so this is your phi, now right eigenvector matrix. Similarly, we can find the left eigenvector matrix by taking, we know under normalized condition phi into psi equal to identity matrix. So therefore, I can find psi equal to phi inverse. So just taking the inverse of this matrix, we'll find adjoint of phi by phi, determinant of phi. That will give me this, right? This is your psi. So now we have the right eigenvector matrix and left eigenvector matrix. Therefore, now I can find the participation factor matrix. So your participation factor matrix will look like this. Now substituting the values, we'll find the participation vector, participation matrix as this. Okay. So if we'll add this particular row or particular column in a uh, in this matrix, participation factor matrix, it will lead to 1, right? Approximately 1. So so the time response, if we'll now if we'll find the time response, we can directly write the equation of the time response. We know that your xt is nothing but equal to phi zt, and zt we know zt is equal to zo e to the power lambda it, right? Zit. So just by substituting this, I can write uh, the state matrix in terms of the new state variable, and that too that is multiplied with the phi, right? Right eigenvector matrix. So therefore I can write delta omega t delta omega. So this is based on x equal to phi z, right? So based on this, so x is nothing but delta omega t delta delta t, and phi is nothing but the right eigenvector matrix, and z is nothing but we know c1 e to the power lambda 1t and c2 e to the power lambda 2t. So now if we'll x, we know phi 11, phi 12, phi 21 and phi 22. We can substitute these values here. And in order to find these constants C1 and C2, we need to substitute the initial conditions. Just by substituting the initial conditions, we can find the values of C1 and C2, and then we can substitute it again in this equation, right? So now the initial conditions are given here at t equal to 0. Delta delta, that is change in the rotor angle or load angle, will be equal to 5 degree. In radian it is 0.0873 radian, and delta omega r is 0 at t equal to 0. So now substituting these values, we can find C1 C2 will be equal to this, because inverse of this right eigenvector will be your left eigenvector into multiplied with the initial condition of delta omega r and delta delta. Okay. So now substituting the initial conditions, we'll find C1 and C2. C1 and C2 are nothing but these are the values of C1 and C2. Okay. Now just by substituting C1 and C2 here in this equation, we'll find the time domain response for delta omega r and delta delta t. That is what we can find the time response of speed deviation. So here in this equation, just some simplification is assumed here, and after assumption and manipulation, we got this. This is the equation, or this is the time domain response for delta omega r. Similarly, the time response for the rotor angle deviation is this, right? Now from these two equations, what we are observing, we can observe here that this is a time decaying oscillatory response, right? it is oscillating at a frequency of 6.35 Hertz. Both delta omega and delta, right? That means your frequency of oscillation will be 6.35 by 2 pi f. It is coming around approximately 1 hertz approximately. So your frequency of oscillation is around 1 hertz, and this oscillation is in fact decaying a manner of at a time constant of 1 by 0.714, right? Time constant 1 by 0.714, right? So therefore the oscillation is decaying, and it is finally the system will become stable, right? So this is what it is mentioned here. So this is a second order system with an oscillatory mode of response having a damped frequency of 6.35 radian per second or 1.0101 hertz. The oscillations decay with a time constant of your oscillation frequency of oscillation is 1.0101 hertz. The oscillations decay with a time constant of this corresponds to a damping ratio of 0.112, and as this is a rotor angle mode, so delta omega and delta delta participate in it equally, right? You will see the participation factor matrix here. This is your participation factor matrix, where we can see that it is 0.5, right? 0.5, 0.5. So the participation of delta omega r and delta delta is in fact equal in equal division, right? So therefore equally they're participating in this mode, right? So the mode is rotor angle mode. In fact, we'll discuss more on this single machine infinite bus system in the next class. So thank you very much. Thanks a lot.